In this course, everything that we've done so far is relating to combinational logic, where we have time-independent functions that are only concerned with the current inputs. Now we're moving into sequential logic, where inversely we have time-dependent circuits, and those circuits are concerned with the current inputs along with the past inputs. So there's 3 devices that we're going to investigate in this video and the next video. That being said, the first device we want to look at is an SR flip-flop. Now, if you look up an SR flip-flop online, look up the circuit diagram, you get a few variations. One of the variations is presented here, where we have an input S, and we have an input R. We have outputs Q, and then Q bar. So Q bar is going to be the inverse of this output Q. Now what we're going to do is just draw a box around these gates, as we're not too concerned with what's going on inside the box. We're going to represent that as this symbol here. We just have inputs S and R and outputs Q and Q bar with a box. Now we have a few rules given by what values S and R take. So if S and R both equal 0 or low, the output Q does not change. So the new value of Q is equal to Q. So if Q was a 0, it will remain a 0. If Q was a 1, it will remain a 1. If S equals 0 and R equals 1, Q equals 0. So depending on what the value of Q was before, if R equals 1, Q new is equal to 0. And if S is equal to 1 and R is equal to 0, Q equals 1. Now the combination of S and R both being equal to 1 or high is an invalid condition. It doesn't work. That being said, we can make a truth table where we can have our inputs S and R and our outputs Q, and we can fill it out as the following, where for the 0, 0 term, we're not changing, so it is equal to Q, and then the 1, 1 term we cannot have. But we can expand this truth table simply considering the past value of Q and then have Q new. That makes the truth table a little bit more digestible, but we still have these invalid terms here. So this is what we're going to consider. Now, because we need to know what the past value of Q is, we have to introduce something new. And that's going to be a time diagram. Horizontally, left and right, that's going to be time. And for each signal S and R, we're going to have it taking place either a 0 or a 1. So S and R will be changing with time. Now what we want to concern ourselves is what the output Q looks like as a function of time. So to do that, we're going to initially assume Q is low by convention. And we have some events that take place during this time where we have S going high and low, and we have R going high and low. So we're just going to have some vertical lines to distinguish when those events occur. So we can drag our truth table down just so we have a reference. And what happens is when S goes from low to high and R is equal to 0, we have this condition here. So we would have Q going to 1. So following along with time as we get to the next condition where S goes low and R is still low, Q does not change, and it holds that value until the third condition when R goes high. So then while R is high and S is low, we will be in a 0 state for the output. And once R goes low at this position here, we'll have the 0, 0 case again. So Q will not change. Now after the 0, 0 right here, we have S going back to high, and this will set that output Q equal to 1 again. Now when S goes to low, we have R also equal to low, so we're going to have no change in the state. And after R goes high, while S remains low, we will reset that state to 0. So this is what our time diagram looks like. Now we didn't put in vertical lines in these transitions, and we'll get to that a little bit later on, but just to understand the general concept, this should do. So now we're going to introduce a clocked version of the SR flip-flop. Now when the clock is low, the state of Q will not change. Only when the clock is 1 is when we will follow the original truth table that we derived above. So this clock signal is just a periodic signal that goes from low to high. So what we want to concern ourselves with is what's going on inside of these clock pulses. So we have 4 of them. Now initially Q is going to be equal to 0, and it's going to stay 0 until the clock pulse is 1. So now that we are inside of the clock pulse, the device will function as derived above. So because S is high and R is low, we're going to set Q equal to high. And then for this clock pulse, when it's off, Q isn't going to change. So in that next clock pulse, we can see that S is low and R is high. So we're going to reset that value to 0. But notice inside of this clock pulse, R goes to 0. So we do have to consider the case when S is 0 and R is 0. Thankfully, nothing changes. Now when the clock is off, Q will not change again. And for the third clock pulse, S and R will be equal to 0. So Q does not change. So we'll be in the same state all the way till the last clock pulse. In this last clock pulse, S is equal to 1 and R is equal to 0. So we'll flip Q to 1. And then because Q is not changing when the clock goes low, we will end up with Q being high. So now we can concern ourselves with rising edge and falling edge events for flip-flops. Now it's common that a flip-flop is either triggered by a rising edge or a falling edge, which means an event will only change, or Q will only change, on each of the rising edges of the clock pulse or the falling edges. So the second device we want to concern ourselves with is the JK flip-flop, and we're going to be concerned with a clocked version of that. Now this is similar to the SR flip-flop, but what differs is when J and K are equal to 1, the value for Q flips, or we can say Q new is equal to the inverse of the previous Q. So that allows us to write a truth table for J, K, the current output Q, and the new output that we should expect. So from this, again, we can look at a time diagram where we're just going to be concerned with the output Q. Now we could care about what Q bar is equal to as well, but for simplicity, we're just going to concern ourselves with Q. And for this example, we're going to have a falling edge JK flip-flop. So we're going to be concerned with what happens at the falling edge of each of these clock pulses. So we have 6 of them, so there should be 6 events. So if we advance to that first clock pulse, you can say that J is equal to 1 and K is equal to 0, which means Q would go to 1 and it would stay 1 all the way until the falling edge of the next clock pulse. And from there, J is equal to 0, K is equal to 1. So we know that we're going to flip back to Q being 0. So going to the third clock pulse, we see that J is equal to 0 and K is equal to 0, so no change. And making our way to the fourth clock pulse, we see that J is equal to 1 and K is equal to 1. Now this state would mean that Q is going to flip. So we're going to go from 0 to 1. And then in between those clock pulses, you can see some stuff is going on, but we only care about that falling edge. And at that falling edge, we have J equal to 1 and K equal to 0. So we are going to keep Q in that high state. And then at that last falling edge, J and K are both equal to 0. So again, we're going to keep Q in that high state, and that's going to finish off our time diagram.